In exercise 8-9, we're going to be drawing the mechanisms of some E2 reactions. And they say for each of the following elimination reactions, so we know it's an E, and then it says a concerted process. And concerted means all of the electrons are moving at the same time. It's not happening one step at a time. So the movements of electrons that we've talked about for elimination reactions, for E2 reactions, are loss of a leaving group and proton transfer. So those two patterns are going to be happening at the same time. Just like in a concert, musicians play at the same time. In this concerted process, these two arrow pushing patterns will happen at the same time. And so that's how we know that it's an E2 reaction. So just by reading the problem that way, we'd be able to say, okay, this is E2. Now they give us the reagent and they give us the product. When they're asking for the mechanism, when they ask you to draw the mechanism, they're asking you to go step by step and show these curved arrow patterns that describe how you get from the reactants to the products. So we'll start by drawing our molecule. Okay, and then our base. So remember, in these elimination reactions, you have two things. You have the substrate, which has the leaving group on it, and then you have the base. Now the base here is really just the OH. Now remember, you have this metal, sodium. You have a metal and a non-metal. That's the sign of an ionic compound. So this is really Na plus and OH minus. So it's the OH minus with the three lone pairs on that oxygen that's going to act as the base here. Okay, so unlike with a substitution reaction, these elimination reactions happen when the base steals a beta hydrogen. The carbon that's bonded to the leaving group is the alpha carbon, first letter in the Greek alphabet. Every carbon one more atom away from that is the beta carbon. And that's the second letter of the Greek alphabet. So this carbon is a beta carbon, this carbon is a beta carbon, and this carbon is a beta carbon. If you're at the alpha, the next one over would be a beta. So the beta carbons are two atoms away from the leaving group. Now those beta carbons can have hydrogens on them, and those are the hydrogens that the base would steal. So you could steal these beta hydrogens. Now the ones that I've already drawn, these have more. These are methyl groups, so they really have three hydrogens. But I'm just going to draw one of them so that it doesn't look as messy. So these are the three possible beta hydrogens that the base could steal. Now the base is only going to take one of these to get our product. So to know which one, we have to look at our product. Notice that in the product, the double bond goes toward the ring. And that means that you would want to steal the beta hydrogen that's toward the ring. So that's the beta hydrogen we're going to keep. The other ones I'm going to erase just for clarity so that they don't confuse us. So I knew that the base is going to steal this one beta hydrogen that's left standing because that's where the double bond appears. It appears toward that beta hydrogen in the product that they give me. All right, well, you have proton transfer. The base steals the hydrogen. The electrons for the hydrogen go toward the leaving group and push it off. The reason why why the electrons are attracted to this position in the first place is because there's a polar bond there. Chlorine is electronegative, so it's slightly negative. And this carbon here is slightly positive. It's losing its electrons to the chlorine. And so when this base tries to steal this hydrogen, the electrons have a natural place that they're attracted to. They're attracted to that positive charge there. Okay, so you have a base stealing the beta hydrogen, the electron's going to kick the leaving group off. And so that gives you your product. So the answer is really this whole thing, all these curved arrows, the correct beta hydrogen drawn in, this whole thing. All right, let's try to do the same thing here. Now, there are a couple sort of symbols here that are standing in for larger molecular structures. So the first thing, let's talk about what this OTS is. So it's called a tosylate group, and what you want to remember about it is that it's a really good leaving group. You want to look at it and think, oh, like a halogen. It's actually an even better leaving group than the halogens. What it looks like if you expand it is you have this big sulfur thing, and then that's connected to a ring, and you've got that methyl group there on the other end. So this O is the same as the O here, and the TS is describing the rest of this whole thing. Now, the reason why this is such a good leaving group, if you're ever unsure and you're thinking, I don't know if this is a good leaving group or not, take the electrons, put them onto the leaving group, and see if they're stable. Because if they are, then it's a good leaving group, and if they're not, then it's not. So if you have the lone pair there going onto that oxygen and bringing a full negative charge onto that oxygen, remember there are two other lone pairs already on that oxygen. That red lone pair, that new lone pair that's adding the full negative charge onto the oxygen, is allylic to 1 pi bond, 2 pi bonds, and then if you draw the resonance structures, you would see that it would be allylic to these pi bonds in this ring also. A nice pattern to remember is that if you have an allylic lone pair, and the pi bond that it's allylic to is conjugated with more double bonds, so alternating double, single, double, single, double, single, that's what it means to be conjugated, then the lone pair will spread out over all of those atoms. It should make sense. That lone pair can exist in a p orbital. To have the pi bonds here, there have to be parallel p orbitals, and to have these pi bonds parallel p orbitals. And so these electrons can spread out through all of those parallel p orbitals. So it's able to stabilize itself a lot by spreading itself out, and so that this is a very stable molecule, and so these electrons can go onto it very easily. So that OTS is called a tosylate. And you'll see it every once in a while, and when you see it, you just want to think, that is a good leaving group. Okay. So that's that. The other thing we've seen before, it's this ET. ET is just standing for an ethyl group. So we have the metal here, again, sodium, very low electronegativity. It gives its electrons away to whatever it's bonded to. In this case, it's going to be the oxygen. And that gives us this ionic bond. Now the ET is going to be CH2CH3, an ethyl group. So here, that ET is that group right there. And if you had to describe that oxygen, that's this one here. Okay, so those are the sort of symbols. Otherwise, the process is very similar to what we were thinking of before. First, draw the molecule. We know that we're going to have the two steps. We're going to have proton transfer and loss of leaving group. And we know that they're going to happen at the same time. Okay, so this is our leaving group. We know that's going to pop off, and that's going to happen when the base, which is this negatively charged group here, and the name for this is called F oxide, F for the ethyl group, and then oxide for the oxygen. So this whole molecule was sodium ethoxide. So you're going to get the leaving group getting kicked off when the ethoxide molecule comes in and steals a beta hydrogen. Now the carbon that's bonded to the leaving group is the alpha carbon. Each carbon that's one atom away is the beta carbon. So here we have two of those. But notice this molecule is symmetric. There is symmetrical, and so there's a line of symmetry. So these two beta positions are actually the same thing. They'll give you the same molecule. If you do a reaction to this side, we'll flip it over as if it's a pancake, and it'll turn into that side. So they're really the same position. But if we want to be completely consistent with what's given in the problem above, I should say, beta carbons, on those beta carbons there are hydrogens. Now technically there are 2 on each one. We're only going to steal one of them. So I'm going to focus on that one and erase the others. If we look at the product that they give us, we see that the double bond is going sort of up. And so we want to take the beta hydrogens that are going in that same direction. So I'm going to erase this other one. I'm going to erase those, erase that beta so it's not as confusing. And the base is just going to take one of these. So I'm going to erase the other one. It's still there, I just don't want it to look confusing. Okay, so I can take the ethoxide, the ethoxide is going to steal the hydrogen. The electrons will go toward the slightly positive charge. Remember, this is a polar bond between this carbon and the leaving group. That oxygen is really electronegative, so it steals electrons for itself and makes that alpha carbon slightly positive. So when the base steals this hydrogen, the electrons feel the pull of that positive charge and go to form a pi bond towards it. And that kicks the leaving group off. So here we have proton transfer. Here we have loss of a leaving group, and they're happening at the same time. And when that happens, you end up getting your product. And actually, and that is the full mechanism for this E2 reaction. Okay, so we're going to do this again, and our 2 essential steps are loss of a leaving group and proton transfer, and those need to happen at the same time in an E2 reaction. So we will draw our molecule. Now this Me here is a methyl group. You notice the metal and the non-metal. Metals have very low electronegativity, so they give their electrons away to whatever they're bonded to, in this case, the oxygen, and so the oxygen gets the full negative charge. Now, in this case, the Me is a methyl group. Oops. A methyl group is a CH3, so that's really just a CH3 there. And, of course, that O is this oxygen here. So that's the name for this is methoxide. Meth because you've got this methyl group, and then oxide because you have the oxygen with a full negative charge. And so the name for this whole thing is sodium methoxide. So this methoxide is going to act as a base. Now when it acts as a base, what hydrogen does it steal? Bases accept H pluses, so which hydrogen? It's going to steal the beta hydrogens, the carbon that's bonded to the leaving group. So this carbon here, that is the alpha carbon. Every carbon one more atom away is the beta carbon. So here we have 1, 2, 3 beta carbons. Now we can tell which one. Was taken, it lost its hydrogen based on the position here. So it's the one sort of going to the bottom left. Now the truth is all of these are the same. They're all the same distance away from the same features. And so there's symmetry here, and all of those methyl groups are sort of the same. So it doesn't really matter in this particular exercise which one you take, but we might as well try to stay consistent with the drawing they give us above. And so I'm going to include just this one down here, because that's where we see the double bond. Now the beta carbons don't do much. It's the beta hydrogens that get stolen by the base. Remember, this bond is a polar bond. Bromine is really electronegative, so it's slightly negative, and the carbon next to it is losing electrons to bromine, so it's slightly positive. So when this methoxide base comes in, it steals that beta hydrogen, and the electrons that are left are attracted to the slightly positive charge. from the dipole. And so they go to form a pi bond toward that. Now that kicks this awesome leaving group off. So we have our two steps. We have loss of a leaving group here with the methoxide stealing the hydrogen, we have proton transfer here with the methoxide stealing the hydrogen and the electrons for the hydrogen going to form a pi bond. And we have loss of a leaving group, and those two are happening at the same time, and that's what makes this a concerted process, an E2 mechanism. So in this case, we would have, now I'll draw it first just how we sort of have it there. It might look like that, right? If you zoom in on this portion of the molecule and you only make the difference of the pi bond, it would look like that. But that wouldn't be the best way to draw that, because these carbons in double bonds, those sp2 hybridized carbons, are trigonal planar. So you want it to look like a triangle. So really, a better way to draw it would be, you have that triangle there with the double bond in it. So if you need to draw this as a first step, just so you can follow along with your original structure, that's fine. But try to draw the double bonds as trigonal planar, like you have over here. So that is your mechanism. We used curved arrows to show the loss of leaving group and the proton transfer happening at the same time. Okay, that's how to draw a basic